Greetings once again. Let's look at another question from exam question paper. So here they're saying a stationary listener, right? So let's keep note of the things. So this is stationary listener. That means the listener is not moving. Standing on a side road, records a wavelength of sound emitted by a siren of a police car traveling at a constant velocity. Okay. So now that means the car is moving. So in the wavelength time graph below, not drawn to scale, lambda L is the wavelength of the sound recorded by the listener, and then lambda S is the wavelength of the sound emitted by the siren. Okay, take the speed of sound in air as 343 meters per second. Coolies. So now they've asked us here what phenomenon or named a phenomenon that explains why the wavelengths shown in the graph differ. So that phenomenon can be nothing other than Doppler effect. Okay, that's the phenomenon effect. Coolies. Now let's see the next question. So here they're asking us, is the car moving towards or away from the listener, and give a reason for the answer. Okay, so this one, then you have to think in terms of these two wavelengths that they've given you here. Okay, that's how you're going to get it, right? And then hence your reasoning from here. Okay, so now this is the wavelength of a listener. This is the wavelength of the source. Okay, so now what you need to think about is, how do you actually translate wavelength into frequency? Okay, so now let's take this for an example. So we've got a wave here. So actually, let me draw it here. So you've got a wave, this wave here, and then you've got this wave here. Okay, then when we want to see a wavelength of these two waves, so now you've got this big wavelength. A big wavelength, you can see that it means less frequency here. Okay, less frequency, right? And then here we can see that we've got a low wavelength or a small wavelength. This is your lambda here. So that means this lambda here, we've got, this is like high frequency here. Okay, this is high frequency. So now that means this listener here is getting less frequency. You can see here. So now the frequency of the listener is actually less than the frequency of the source. Okay, should be something like so. Now I've only just used these two graphs, so I can already see that the source actually has a bigger frequency, whereas the observer, the listener, is receiving less frequency. What does that mean? So this means the car is moving away, okay? Because the source has higher frequency, but what is getting to the listener is less. So the listener is only getting less sound. So that means what we can then say is that it's away from the listener, okay? Yes, it's away from the listener. So why is that? It's because the listener is getting less frequency compared to what the source is actually generating here. Okay, so you can put it in simple English and also put it like so, or use the wavelength. So any of which makes sense to you or is easy to understand. But now when you dealing with your wavelengths, you can translate them into frequency, so then it's easy for you to deal with, right? Or draw the graphs like I just did, so that it makes sense. Okay, and then we've got the next question that asks us to calculate the frequency of the sound emitted by the siren. Right, now how do we then calculate that? Okay, so we've got a formula for this. It's pretty much straightforward. So that means for 6.3.1, you're going to say V is equal to the frequency times your wavelength. So they've already given us the velocity, which is the velocity of the sound. They've already given us the wavelength also. So that means we just need to get the frequency. Okay, so with regards to the velocity is 343 being equals to your f, then times our wavelength. We're going to use the wavelength of the source, which is this one here. So that is going to be 0.38, then divide by 0.38, divide by 0.38. This goes away, then you are left with f. Okay, now let's see from our calculator what we get. Okay, so from my calculator, I'm getting 902.63 hertz. Okay, this is the frequency of the sound, right? So, and then the next question then ask us, let's see, what do they need from us? They're asking us to calculate the magnitude of the velocity of the car, right? Bit interesting. So here, what do we need to do? Okay, so think about it a bit and then apply yourself. So one of the things to do here is, let me just do this 0.3.2. So what you need to do here is, you've got your formula for Doppler effect plus minus VL all over V plus minus Vs times Fs. Okay, so here what we've got from this, we've got Fs. This is Fs. So here we're looking for the velocity, but that means in this case we don't have Fl, okay, the frequency of the listener. So that means we need to first calculate that the same way that we are calculating this one here, Fs. Okay, so that means I need to just come here and say I've got V being equals to F lambda. Okay, so again it's the same velocity, then the frequency is what we're looking for, but now we're going to use the wavelength that is of the listener. So it's going to be 0.4, like so. Then we divide by 0.4, 0.4. Okay, then now you've got your FL. Let's punch our calculator. So I'm getting 8557.5. Okay, 0.5 hertz. So now we've got two of these, so that means we can simply go and substitute so that we're able to calculate the velocity of the car. So the velocity of the car is going to be what? The velocity Vs here. Okay, so let me just copy this to the other side. Okay, so this is where we are now. Okay, so what we need to remember is that, so I've given all these this data. So what we need to note is from the question, it says here the listener is stationary. So that means the velocity of the listener, which is your VL, is going to be 0 meters per second, right? Then Vs is what we are looking for, and we've gotten V, right? So now we need to then decide we need to decide about our signs. Okay, so first things first, let's just do something like so. So this is going to be V plus minus, since this is 0, then we've got plus minus Vs here, okay, times S. So here that means this is going to go away. So what you're gonna have is V over V plus minus Vs like so, times Fs, right? So then we need to then decide what is going to be the sign here. Okay, so now since the car is the one that is moving away, we are going to have a positive one here. So that means what you're gonna have is, let me use this color here. So what you're gonna have is FL is equals to V, then V plus Vs, then times Fs. Okay, please visit one of there's a lesson on this, on how to choose your signs. So I've written all the conditions for this. Okay, right. So now that you are here, it's easy for you to just substitute all this data here. So we can say 8 7.5, which is the frequency of the listener. V would have already given us is 343. 343, then 343 again, plus Vs is what we are looking for in this case, right? Then you're going to have what? 0.902.63 hertz. So now that you are here, it's pretty much easier for you. So you can manipulate this and then you get your answer. Okay, right. So let's see what we get. So to make things a bit easy, so we can maybe, let's say we divide here by 902.63. 902.63. This will go away, right? Because it's multiplication. And then let's see what we get from here. So, okay, so I've simplified it. You end up with 18.05 meters per second. Okay, and that is the velocity of the source, which is the velocity of the car. Okay, so that's where it ends. Thank you guys. Let's meet next time.